Hey you guys, this is Mr. Millings, and today we're going to learn about colligative properties. So what are colligative properties? Well, it says right here that colligative properties are properties of a solution, example being boiling point, freezing point, vapor pressure, and osmotic pressure, that depend on the amount of dissolved solute particles in the solution. So what does that mean? Let's suppose we have two beakers here, and each one of these beakers has some sort of dissolved solute in it. This one has some salt, and this one has some sugar. And we know from prior experience that when you put salt and water and sugar in water, they dissolve. You stir them up and they dissolve, right? Well, what happens to the boiling point, or what happens to the freezing point of aqueous solutions when you place them in water? Well, what we're going to learn is that when you place a dissolved solute in water, it's going to increase the boiling point of that solution, and it's going to decrease. So the freezing point of this solution here is going to decrease. So normally we know that water has a freezing point of 0 degrees Celsius, right? The freezing point of H2O is normally 0 degrees Celsius, assuming we are at sea level. The boiling point of water at sea level, or at 1 atmosphere pressure, is 100 degrees Celsius. So if we take a look here, when we dissolve something in water, either salt or sugar or anything for that matter, it's going to increase the boiling point. So this solution is no longer going to boil at 100 degrees Celsius. It's going to boil a little bit higher, and how much higher depends on how much of this stuff we put in it. And same thing with the freezing point. The freezing point of water is normally 0 degrees Celsius. However, once we start dissolving stuff in it, whether it be salt or sugar, ionic compounds, or polar covalent compounds, the freezing point is going to decrease. So this solution is no longer going to freeze at 0 degrees Celsius. It might freeze at -5 degrees Celsius or -6 degrees Celsius, depending on how much dissolved solute is in the solution. So colligative properties are properties of a solution that depend on the amount of dissolved solute particles in the solution. Okay, so the boiling point and freezing points of these guys really depends not on the chemical makeup of these substances, but how many dissolved particles are in the solution. The more dissolved particles you have, the higher the boiling point and the lower the freezing point. Okay, so it's important to understand that colligative properties do not depend on the type of chemical species present. Rather, they depend on how many dissolved particles are in that solution. And in this little video, we're going to focus our attention on boiling point and freezing point. But understand that colligative properties are properties of a solution, such as vapor pressure and osmotic pressure, that depend on the amount of dissolved solute particles in the solution. So let's take a look at a couple of examples here. All right, so we have 3 beakers of water here. And in this beaker here, we have some sugar that we're going to dissolve in here. We're going to put some sugar in here, and we're going to stir it up, and we're going to dissolve it. And we're going to throw some sodium chloride or table salt in here. We're going to stir it up, and it's going to dissolve. And last but not least, we're going to put some potassium sulfide in here. We're going to stir it up, and it's going to dissolve. Okay? And the question that I want to ask is, which one of these will have the greatest difference in boiling point, and which one of these guys will have the greatest difference in freezing point? Well, to answer that question, what we first needed to look at is whether or not the substance is polar or ionic. That plays a big role in determining this question or answering this question. If we take a look at sugar, we talked about sugar earlier this unit as being polar covalent. It is a polar molecule, so when I put sugar in water, it does not dissociate. It's not going to break apart. So when you put this substance in water, it stays intact. It still dissolves because of the hydrogen bonds between the oxygens and hydrogens here. However, it is not going to dissociate. Okay, so that is what polar compounds or polar molecules will look like when you put them in water. These two guys, this salt here and this salt here, we learned from a prior or earlier video that when you place these in water, they dissociate. They break apart into the ions that make them up. So when I put this salt in water, it's going to break apart into a bunch of sodium ions and a bunch of chloride ions. And when I put this salt in water, because it's ionic, it's also going to break apart or dissociate into the ions that make it up. It's going to dissociate into a bunch of potassium ions and a bunch of sulfide ions. Okay, but let's take a look at what happens. Let's suppose I have 1 mole of NaCl and I put this in this water right here. It's going to dissolve and dissociate. And when it dissociates, what ends up happening is it produces 2 moles of dissolved particles. Whereas over here, if I have 1 mole of sugar and I dissolve this in water, I still end up with 1 mole of dissolved particles. Okay, so understand that concept. When something dissociates, it breaks apart. So 1 mole of salt is going to end up producing 2 moles of dissolved particles. And if we take a look at this right here, at potassium sulfide, if I put this in water, it's going to dissociate. And if I have 1 mole of this, it's going to dissociate and produce 3 moles of dissolved particles. The 2 right here, the 2 moles of potassium ions and the 1 mole of sulfide ions. Okay, so this is an important concept to understand. So if I were to ask you which one of these guys or which one of these solutions here is going to have the greatest effect on boiling point and the freezing point of the solution, it's going to be this, because there are 3 moles of dissolved particles. Which one will have the least effect on its boiling point or freezing point? It's going to be the sugar, because there's only 1 mole of dissolved particles. So it's an important concept to understand that if something dissociates, if an ionic compound dissolves, it's going to dissociate, it's going to break apart, it's going to produce more moles, and therefore it's going to have more of an effect on the boiling point and freezing point of that solution compared to a polar substance. So let's take a look at how we can calculate changes in boiling points and changes in freezing points depending on the amount of dissolved substances in that solution. All right, if we take a look at this example here, or if we take a look at this formula here, what we're looking at is we are looking at a formula that allows us to determine changes in a solution's boiling point. All right, so to calculate a change in the boiling point of a solution, it's simple. We take the boiling point constant of water, which is 0.512 degrees Celsius per this lowercase m here, which means molality of the solution, which we learned in an earlier video. We then multiply it by the molality of the solution, and then we multiply it by this right here. I is the Van Hoff factor. You can think of this as the number of particles the substance will dissociate into. And we're going to use this specifically for ionic compounds or electrolytes. So let's look at this example, and hopefully you catch on. In this example here, of a 1.5 molal aqueous solution of sodium chloride. We're going to assume we're at sea level, so pressure doesn't come into play here. So to calculate the change, we want to calculate, we first want to calculate, or we want to calculate the boiling point of this solution. In order to do that, we must find the change in the boiling point temperature. So to do that here, to get delta T, to get the change in the boiling point of this solution here, we take, since we're dealing with water here, it says it's aqueous, right? It says it's aqueous. We take this boiling point constant of water, 0.512 degrees Celsius over lowercase m, which stands for molality. We're then going to multiply this by the molality of the solution. Well, it says right here the molality of the solution is this right here. The molality is 1.5 m. And last but not least, we need to multiply this by the Van Hoff factor. And let's think about this. If I put this in water, it's going to dissociate. And if it dissociates, it's going to break apart into 2 different ions, right? So the Van Hoff factor here is going to be 2. So we'll multiply this by 2. And we'll get our calculator out here. And we end up with 1.5. degrees Celsius. So this isn't our final answer. This is just the change in the solution's boiling point. All right, we know that water normally boils. The boiling point of water is normally 100 degrees Celsius at sea level. And so we need to add this 1.5 to it. And we will end up with 101.5 degrees Celsius. So what will the boiling point be of a 1.5 molal aqueous solution of NaCl, assuming that we're at sea level? It looks like this water, or this solution of salt water, is going to boil at a temperature of 101.5, right? The boiling point has been changed by a temperature of 1.5 degrees Celsius. Let's take a look at this example here. What if we have the same molality here? We have a solution of salt that has the same molality, and we're asked to calculate the boiling point of it, except this time, take a look. We have a different type of salt. We have calcium chloride. We're going to assume that we're at sea level. So once again, to get the change in the solution's boiling point, we take the boiling point constant, 0.512 degrees Celsius per molality. We're going to multiply this by the molality, which is 1.5. And last but not least, we need to think about this. What is the Van 't Hoff factor going to be here? If we put this in water here, it's going to dissociate. All of these ions are going to dissociate, and we should end up with 3 ions, right? We have 1 calcium ion here, and we have 2 chloride ions here that it's going to dissociate into. So we're going to multiply this by the Van 't Hoff factor, which is 3. I'll put this in our calculator, 0.512 times 1.5 times 3, and we end up with 2.3. So the solution's boiling point is going to be changed by 2.3 degrees Celsius. We need to now add this to the boiling point of water at sea level, which we know is 100 degrees. And we will end up with the boiling point of this solution equaling 102.3 degrees Celsius. Okay, so the final boiling point of this solution is going to be 102.3 degrees Celsius. Let's take a look at a couple more examples using freezing point. Okay, if we take a look here, this is the formula that we're going to use to find the freezing point of a solution. Okay, so to get the freezing point, or to get the change in the freezing point of an aqueous solution, we take the freezing point constant of water, which is 1.86 degrees Celsius per molality, times the molality of the solution, times the Van 't Hoff factor. So this is very similar to what we just were working on. So let's take a look at this example here. Calculate the freezing point of 0.5 molal sugar water solution, assuming you're at sea level. So in this problem here, we want to know what it's going to freeze at, this solution. So we must first calculate the change in the freezing point. To do this, we take the freezing point constant, which is 1.86 degrees Celsius per molality, which it says right here, times the molality of the solution, 0.5, times the Van 't Hoff factor. If you take a look, we're dealing with sugar. Sugar is polar, so it's not going to dissociate. So 1 mole of sugar is going to produce 1 mole of dissolved particles. So we'll just multiply this by 1. We get our calculator out. 1.86 divided by, 1.86 times 0.5, and we end up with 0.93, or 0.9 if we're using the correct number of sig figs, 0.9 degrees Celsius. So this is just the change in the freezing point. We know water freezes at the freezing point of water is equal to 0 degrees Celsius. We're now going to subtract, right? This is a depression. That means to lower. So we're going to subtract this 0.9 here. from 0. And it looks like the freezing point of this solution is going to be 0.9 degrees Celsius. Let's take a look at this example. We have the same molality, however now we're dealing with salt water. So which is going to lower the freezing point more? A sugar water solution or a salt water solution? Well, you can imagine, because the Van 't Hoff factor here is 1 and you know it's going to be 2 here, that salt will in fact decrease the freezing point. So let's take a look here. In order to figure this out, we must first calculate the change in the freezing point. So we take 1.86 times the molality of the solution, which is 0.5, times the Van 't Hoff factor. If you put this in water, it's going to dissociate and produce two different particles, right? It's going to dissociate into sodium ions and chloride ions, so two different particles. And if we put this in our calculator, we should end up with 1.86. Or if we use the correct number of sig figs, we'll ignore the sig figs for this problem. We'll just say 1.86. So this isn't our final answer. To get the freezing point of this solution here, we will take the freezing point of water, which we know at sea level to be 0 degrees Celsius, and we'll subtract 1.86, and we will end up with negative 1.86 degrees Celsius. Whoops, this should be negative 1.86 degrees Celsius. Okay, so which one is going to lower the freezing point more? Sugar water or salt water? It looks like salt water is going to, in fact, or the salt is going to lower the freezing point more. And in fact, most of the salt in the United States is actually used on icy roads because it lowers the freezing point of that water, prevents that water from freezing, and prevents many accidents. So these are colligative properties, and I hope you found this helpful.